Hi everyone, welcome to Flammable Maths. Today we'll be talking about a very comfortable property of a particular class of 2x2 matrices. Consider the matrix 3, 4, 6, 8. Well, some of you seem to know where this is going if you watch the Flammable Maths channel. Yes, I did indeed get the video by watching this channel, and I have been working on the solution for over a week. So even though my video came out after Flammy's did, it does not mean I copied his content. No, you'll find that this method is original. So please stick around. I'll show you the magic trick and we'll get to the solution, okay? And please check out his channel. He is fantastic. I think he's the best math YouTuber out there. So please give him a listen. Magic trick is this matrix squared. Well, let's just evaluate it and see what we get. It's going to be matrix times itself, of course. And we're going to multiply these two. 9 plus 24. 6 times 3 is 18 plus 6 times 8 is 48. 3 times 4 is 12, plus 8 times 4 is 32. Now we have 24 again, plus 8 times 8 is 64. So this just becomes the matrix 3, 3, 4, 4, 6, 6, and 8, 8. Pretty cool, huh? Seems like a pretty magical matrix, or a comfortable property of the matrix, since it was on an uncomfortable math memes page. It is pretty cool. Obviously, it's not going to work for any matrix that we put in. So the goal of this video is to find the 2x2 matrices such that this is true for. The first step to doing this is to realize that the comfortable property is that the matrix that we ended up with is simply 11 times the original matrix. Since, of course, 3 times 11 is 33, and the rest of the components are similar. So we're looking for matrices satisfying this property. And to start out with, I'm going to talk about a similar concept from linear algebra and relate it to our situation here. Okay. Linear algebra tells us that matrix A is idempotent if and only if A squared is equal to A. So we have similar matrices here. We have matrices that if you square them, you get 11 times the matrix. So I'm going to investigate an arbitrary multiplier here. I'm going to be calling 11 just be a discrete variable, so I don't have to keep carrying 11 around because it's really awkward. I'm going to define A to be lambda potent if and only if A squared is equal to lambda A, where we have lambda not being equal to 0. Lambda equals 11 is the case that we're referring to. And I just want to make it clear that in making this definition, there's nothing new theoretically. There are no new theorems to prove, since in fact it's just a constant multiple of an idempotent matrix. We'll show this as follows. Okay. We have A squared is lambda A, which, since lambda is non-zero, we can divide it. We're going to multiply by 1 over lambda squared. So A over lambda squared is going to be A over lambda. So A over lambda is actually idempotent. So yeah, nothing new here. We're not talking about a new class of matrices, just a constant multiple, 1 over lambda, of an already known quantity. And just from our definition of the lambda potent matrices, we can already get one important property. So theorem, small theorem, A lambda potent actually tells us that A transpose is lambda potent as well, since A transpose squared is the same thing as A squared transpose, which is a which is a transpose. And this follows from the identity A, B transpose is equal to B transpose, A transpose from linear algebra. So just from talking about these matrices in general, we already have a new matrix. So far, we have 3, 4, 6, 8, and its transpose. So recall, if we take the transpose, we reflect across the diagonal. 3, 6, 4, 8 are currently 11 potent. But we want to find more. We want to find all of them. So let's get started. I'm going to impose some conditions on the 2x2 matrices such that we can eliminate components in favor of other components and parameterize them so that we can obtain all the possible lambda potent matrices specialized to lambda equals 11. And the reason I want to have a lambda at all is because it's pretty straightforward to investigate other potent matrices, like matrices that if you square them, they are double the original matrix, perhaps for next time. Okay. In general, if we have a lambda potent matrix, let A now be a 2x2 lambda potent matrix, of course. So we have the following definition. Lambda A is going to be lambda A, B, C, D, just find the components. And it is A squared, which is A, B, C, D, A, B, C, D, which we can multiply out pretty easily. A squared plus BC, AC plus CD down here, AB plus BD here, and BC plus D squared here. And continuing, we can break this one matrix equation with 4 components into 4 single line equations. So we have lambda A is equal to A squared plus BC. Lambda B is equal to AB plus BD. Lambda C is equal to AC plus BC. And lambda D is equal to BC plus D squared. Now hang on a moment. Some of you are going to say, this is exactly what Flammy did on his channel. You're right. So far it's the same. But he actually noticed something that I didn't notice. He found a condition involving the determinants. He found that the determinant of these matrices A has to be 0, and then used it quite straightforwardly to get the integers that satisfy this. Unfortunately, I didn't notice this at the time, so my solution is more convoluted, and it's up to you to decide if there are any advantages. So let's not use Flammy's condition and continue onwards. Okay, this equation here tells us that 0 is equal to B, lambda minus A minus D, which tells us that either B is equal to 0 or D is equal to 1 minus A, lambda minus A. We're going to choose this one since it turns out that no lambda potent matrix actually has any of the components being 0. So this is a good assumption to make. And the second equation is similar. Everything with replaced B going to C. Again, we're choosing this equation, C not equal to 0. We no longer need this equation since we have related D in terms of A, so we don't need it anymore. This equation just tells us the condition that A, B, and C have to satisfy in order to be lambda potent. So that one stays as is for now. You can certainly keep it in this form, or you can solve for C. So if we do that, C is equal to A lambda minus A over b, for c not equal to 0, of course. And there we go. That's all we need to construct the matrix. So now we have that A is equal to, more general form, A, B, C, and lambda minus A, subject to the following condition up there. Lambda A is equal to A squared plus BC. Or it's the same thing as writing A as follows. Have a matrix A, B, and then A lambda minus A over B, and then lambda minus A here. They are the same thing for B, C not equal to 0, of course. Yeah. Great, so we have these two forms of the matrices, so it seems like we're done. But we're not, because notice this component does not have to be an integer. Most of the time it's not. So if for some reason you wanted a matrix that had components like this, and you square it, and it satisfies the multiplying by 11 property, well then you're good. But we don't want that property. We don't care about that property because it's stupid. So we only want the integer solutions of this equation, and that is the hard part about my solution. But let's get started. So we can actually derive more theoretically interesting properties of the lambda potent matrices now that we have the explicit expression. I want to use the fact that for lambda potent matrices there's an additional symmetry. So before we had the fact that you could transpose it and it was still lambda potent. There's another one for the 2 by 2. This only works for 2 by 2 matrices. 3 by 3, no, doesn't work. Don't use it. Okay, so for the 2 by 2 matrices, notice what happens if we interchange, make the substitution, A goes to lambda minus A. If we do this, we're going to have this be put up here and this be put down here. And this one will be unchanged as well. But I'll go ahead and show it to you in general here. So if we have A goes to lambda minus A, in general, we're going to have lambda minus A is equal to lambda minus A squared plus BC. So lambda squared minus lambda A is equal to lambda squared minus lambda A plus A squared plus BC, canceling lambdas. This tells us that we arrive with the same condition, lambda A is equal to A squared plus BC. So if we do this, the matrix is also an idempotent. So basically, we've shown that if we have any lambda potent matrix, we can go ahead and take this X pattern with the components and generate more lambda potent matrices. So far we have the following matrices. We knew 3, 4, 6, 8 from the beginning, explicit calculation. We knew 3, 6, 4, 8 from the transpose condition. And now we have two more with the diagonal interchange condition. I don't know what this is called because it only holds by 2 by 2. It's not really that useful. Okay, so now we have, interchange these, 8, 4, 6, 3. And we also have, if we interchange these, 8, 6, 4, 3. All of these are lambda potent as well. But wait, there's more. Let's say we wanted to consider negative solutions. Well, that's pretty straightforward. We can do that as well. If we let B goes to minus B and C goes to minus C, we will obviously see that we negate these two here, and we need to see, we negate these two. We have to see if the condition is satisfied. So let's see what happens. Yep, lambda A is now equal to A squared plus minus B minus C, which is A squared plus BC. So we're all good. So now we can basically include the negatives by simply negating the signs in the following pattern. So We could negate everything we found here or not to get more matrices, plus or minus everywhere. So what I mean by this is I'm claiming that 3 minus 4 minus 6, 8 squared is equal to 3 minus 44 minus 66 and 88. Don't believe me? Try it for yourself. Go ahead. Okay, people. So now we need to demand that this is an integer so we can start generating more integer solutions to this bad boy. This is the hard part. It's not that bad, but it does involve computers or plugging in lots of numbers eventually. Okay, so I am going to demand that this component be an integer. I'm not going to work with it in this form since we need the explicit numbers here. This has to be an integer. One way to do this is let a over b be an integer, or let lambda minus a b over b be an integer. I'm going to choose the first one because the algebra is slightly simpler. I'm going to demand that a over b is an integer, which we're going to call n. And if we do this, of course, we have a in terms of b. A is just nb. So now we have our matrix A written as nb. And b stays the same. This becomes n lambda minus nb, and this becomes lambda minus nb. Sorry, just for clarity. Okay, and just to make sure that we have the lowest entry in the upper right-hand corner, I'm going to interchange them. Lambda minus nb is going to go here, and nb is going to go down here. I can do this because of the diagonal swap property, so going this way across the diagonal that we talked about. All right, so these are all the integers. That's good, that's good. But there's another condition as well. We also need everything to be less than or equal to 9, all digits. Because if you have 10 times 11 somewhere, it's 110, which does not satisfy the magic trick. So this is actually the harder condition. This was easy. Now basically, unless you want to use a computer, you just have to plug in n's and b's and see if you get this condition. Obviously you can't prove that you get them all this way, but I'm not going to do that. I actually used a computer to just multiply all the 2 by 2 matrices together with this property and found that I had discovered them all and stopped. So feel free to do the same. Okay, now we plug in some specific examples and hope we get lucky. Most obvious example we can think of would be n equals b is equal to 1. If we do this, we have 11 minus 1, which is 10. So we can't use this one because it's going to have a 10 in it. So nope, not going to do that one. Basically, we're going to set n to be fixed and then loop b. That's the easiest way to find these. So we're going to consider the next value for b equal 2. If we do this, we have 11 minus 2 is 9, which is the next one. So our matrix is now 11 minus 2, 9. B is 2. Now we have another 9 here and a 2, which I'm going to write in a standard form for this video, 2299. So we found one more. Fantastic. Let's keep going. If you continue with the n equals 1 series, you find the less interesting matrices that have only 2 numbers in it. If you continue with the n equals 1, you will get the following other uninteresting matrices. We'll have 3, 3, 8, 8, and we'll have 4, 4, 7, 7, and we'll have 5, 5, 6, 6. Those are the other 3 n equals 1. If we go to n equals 2, more interesting case, we are going to show that nothing works for b equals 1, 2, 3. You'll have things that are greater than 10. When we do b equals 4 for this matrix, so 11 minus nb is 8, 11 minus 8, 8, 9, 10, 11, 3. And this will generate the matrix 3, 4, 6, 8. Should look familiar from the intro. Great. So at least it can do what we want it to do. Yep. And now for n equals 3. Incidentally, this is the only less than or equal to 9 matrix for the n equals 2 series. N equals 3 matrix. N equals 3. We also have one solution for b equals 3. We'll have the solution. Let's see, 11 minus nb is 3 times 3 is 9, which is 2. So this generates the matrix 2, 2, 3, 6, 9, I'm pretty sure. 2, 3, 6, 9. Yep, that's the one. So basically the problem is done. I haven't proven it, but I have simulational evidence that this is it. So let's go ahead and write all these matrices in a nice fashion so that we found them all. We're going to celebrate. I think this calls for celebration. I've never heard of these matrices before, never seen them before, never used them in a course, so I think it's cool that I was able to find them all. So was Flammy. His method is a lot quicker. Just celebrate by writing them all first. So, A is the following matrices. We have 2, 3, 6, 9. And we have 3, 4, 6, 8. And we have 2, 2, 9, 9. Uninteresting. 3, 3, 8, 8. And 4, 4, 7, 7. And 5, 5, 6, 6. That's it, folks. And of course, we can do the X pattern that we talked about to generate more. And yep, that's all of them. Go tell your friends. Feel free to show them this magic trick. It is pretty darn cool. That's about all I have to say about lambda equals 11 case, but the other cases are up for grabs. And let's just, yeah, feel free to investigate them by yourself and have a fantastic day. I'll see you next time. Please subscribe.